Okay, good afternoon, wherever you are. Can everybody hear me? Quick sound check to make sure.
Yep, you're fine.
Okay, good, thank you. Today we're going to talk, I don't really have a specific agenda, but basically the plan is to try to answer questions that you might have about this lab, the last lab or the previous labs. And so the approach I'm going to take today is I'm going to walk through the staff solutions, in particular my own solutions, and discuss them. And hopefully, as we go through the staff solutions, you can jump in if I don't answer a particular question, or wait a little bit because I put all the questions that you've asked, at least before 11 a.m. this morning, in the lecture notes at the bottom, and we'll try to go through that. I'm going to start with the page table lab, because most questions were about the page table lab, and partially because presumably it was the hardest labs. And so maybe a couple of comments before diving into sort of the technical part of this. Let's talk a little bit about the page table lab in general. And as you probably observed, it's actually few lines of code in terms of the solution, but unfortunately it has hard to debug problems. And there's one reason is that when actually the bug shows up, the outcomes are pretty extreme. Like in the worst case, probably some of you observed that in the worst case, QEMU just stops, or XV6 just stops. There's no output being printed anymore, and that's it. And now it's your job to sort of figure out actually what went wrong. In the best case, you get sort of a kernel panic. But the panic, may be just a starting point of sort of tracking down what the actual source of the problem is. The panic itself is probably related to something else, some invariant that in the kernel got broken. But somewhere out earlier, probably when you set up the page tables, you did something wrong that in the end caused this panic to go off. And so you have to track down what's going on. So fewer lines of code, hard to debug problems, and just a harsh environment to debug in. If you do in the kernel debugging or kernel programming, just the programming environment or debugging environment is unforgiving, as Robert mentioned in the first lecture. And this is one of the hard parts about basically doing kernel programming. And that's just to make you maybe feel better. This is not just hard for you. It's actually also hard for the staff. Both in terms of helping you and actually, when we do these labs, we make similar problems, and we probably have more experience in tracking bugs down, but they do take time. In terms of helping you, it tends to be hard too, because there's some small fragment of code, there's one detail, something probably wrong, and figuring out actually what that little detail is not that easy. Of course, some of the problems we've seen before and we recognize, for example, we didn't make the same mistake ourselves, but other ones, you discovered all kinds of different ways of sort of breaking the kernel that we hadn't seen before. And so this is just hard. And I think this is in our experience, this is historically always hard with virtual memory. So every time the first virtual memory lab, comes around either in SO81 or its predecessor in 6828, it has been the case that that tends to be the hardest lab of all the labs, and for a number of reasons. One, the harsh environment, the bugs are spectacular, and partly because you haven't had that much kernel programming experience yet, and so this is sort of the first lab where all those things come together. This year, we tried to make the lab simpler. In fact, this is a new lab. Last year, we did not have that lab. in the hopes to actually make this introduction or the transition into virtual memory easier. In some ways, I think it was successful. In other ways, it's still hard. And so we don't really know maybe what the easiest way of actually introducing virtual memory programming is. The lab next week, the Lazy Lab, is actually the lab that used to be the first virtual memory lab. And my suspicion is that you'll find it this year, that lab, easier than the students found it last year, because you now have much more background in virtual memory. Okay, so that's maybe it's a good point to stop. This is like there's a couple of high-level points I wanted to make before jumping into the more technical or the details. So if you have any questions, this is a great time to ask questions. Okay, then let's quickly, some of you asked for this, very quick review exactly what what the sort of the setting is, and so basically the setting is page tables, and we have physical memory. I will draw here on the right side. We know that physical memory consists of partly of devices, and they live above this OX 00, and many more zeros. And then here is basically DRAM chips. And we know that QEMU actually puts the kernel text and data right here at the above OX 0000. So this is where the kernel lives. And one way, maybe let me erase this a little bit. So here's the kernel, and basically literally what it means, what the kernel is, and here are the instructions. The binary versions of the assembly instructions that you have seen, and there's also some data structures located at these addresses. Okay, so that's the memory part of it. Then on the other side, we got our CPU that executes instructions. And so the CPU has a bunch of internal state, and has some registers, whatever, X0 or R0, blah, 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 blah. And, maybe the program counter. And, when x86 starts, the program counter contains this value OX0000. And that's the way, the CPU knows that basically, look at that address to find, the first instruction. It looks at the first instruction, decodes the instruction, and updates whatever CPU state that needs to be updated. Page tables add sort of a component to it. The addresses, that the CPU others, or the instructions, or part of the instructions, like jump to some particular address. Those addresses are typically, or most commonly, or there will be virtual addresses, and those virtual addresses go to through something that typically is called the MMU, and the MMU translates it to physical addresses. That allows us to index into either the I/O part of the memory or the DRAM part of the memory. To control how this translation happens, there's this SATP register, which contains the root of the page table, of the current running page table. And if there's 0, then there's basically no translation going on, and the virtual address is literally directly a physical address. So when the processor actually starts up, there's no value in SATP, and so when the program counter is at OX, basically the physical address is also OX08, and basically the CPU fetches the instruction from that particular location. As soon as the SATP actually contains a non-zero value, then for example, maybe so somewhere in here, so like I'll draw, maybe extend the picture a little bit further. We know that the kernel actually has a maximum of 128 megabytes. And so basically this is all free memory. From here to there is free memory. And the free memory is put on the list in calloc.c, as you've seen before. And so somewhere in here is also the root page table for, you know, a kernel page table. So maybe here's some page, and that is the root page table directory. And as soon as we load that value, you know, the address of the physical address of that value into the SAP address register. So let's say this, you know, maybe this address is OX7, you know, FF, blah, blah, blah. So something just below 120 megabytes. So in that free space of memory, we load that address in SATP. Then at that point, you know, the processor or the MMU will use the root page tables to actually do the translation, you know, from virtual to physical address. And you can think of this, you know, this particular whole thing sort of being a single sort of box, you know, integrated, you know, together. Any sort of questions about this high-level picture before keep on going? So one of the key points that sort of to remember here is that the page tables themselves also live in memory. Okay. Okay, so let's jump then to the first part of the page table app, namely part 1, where you have to print the page table for the init program and you know, explain it basically in terms of this figure 3.4, and the figure 3.4 is right here. It is figure 3.4, and this is figure 3.4 shows the user address space. So just let's look at the user address space for a second before we go into detail. So we have the text at the bottom. So this is the instructions of the program, starting at address 0. Above the instructions are, you know, data, so global variables live there. Then there is something called the guard page we'll talk about, and then there's the stack of the user program. So the kernel has its own stack, but the user, or multiple stacks. Then the user program has its own stack. And above, again, is basically what's called heap memory, you know, free memory, you know, that we can, you know, get more memory using sbreak. So sbreak basically points to the top of the user address space, and if we want to grow it, we call the sbreak system call to grow the top of the, to grow the bottom part, you know, up into the heap. And we also know that at the top there from the last lecture that there are 2 pages, 2 special pages, the trampoline and the trap frame page. And the trampoline page, you know, contains these instructions to basically transition in and out of the kernel, and the trap frame is a convenient place, you know, to store some state when we jump into the kernel, because we need the kernel wants to use the registers. We can't use the registers because the user space program still has them in use. So I'm not going to talk much about the tramp frame and the trampoline at all, but, you know, they're there. Okay, so here in this picture a little bit below, you know, is actually the printout from when I ran it from init. This is the first successful call of exec, right? So like we know that init code makes some system call exec for the program init, and just at the end of exec, we're printing out that page table. And so there's a couple things that we, you know, many things we can observe about this particular page table. So first of all, you know, we, in addition to printing out the physical, the PTEs and the physical addresses, I'm also printing out the flags. And you know, you can see here that here's the flag is 1, and that basically says that this translation or this intermediate page is valid. Similar here, that is an invalid intermediate page, and these basically correspond, you know, to the level 2 page, and then the second one corresponds to the level. Sorry, I just drew the arrows wrong, so that's why I paused for a second. Okay, so the top, this is the top level page table. This, you know, points to this particular page table, and then this, you know, points to that particular page table, or that's the address, you know, pointing to, you know, sort of a shorthand for saying that is the base address for that particular page. And as you know, each of these pages is 496 bytes. That's the size of the page size, and so divided by 64 bits, you know, you get 512 entries. Okay, so what we see is that the bottom part of this address space for init basically has, actually all this, has 3 pages, only 3 pages. And we got a couple of things that we can discern from the 3 pages. We know that the bottom page, which basically corresponds to virtual address 0, lives at physical address 87640. And we know from our previous picture that is somewhere in that free memory that the kernel has available to allocate pages from. And then the final thing, we see the flags. And we see the flags have 1F. So it means that the read bit is set, the val bit is set, the read bit is set, the W bit is set, the execute bit is set, and the U bit is set. So this page can contain both data and text, and these permissions allow the user program to execute instructions from it, read or write memory, and do it from user space. Okay, so then maybe the most interesting question is like, what's up with page 1? And as a hint, we see that page 1 only has F and not the U bit set. So what is page 1? Anybody?
Is it the guard page?
Yeah, it's the guard page, right? So the guard page is mapped because it has a vmip, but it has not the U bit set. So any user instruction that tries to, so if a user program runs off its stack, so the stack grows from the top down. So if it actually has more, the stack is bigger than 496, it's completely full. And if then the user program, pushes something on the stack going down, it will grow into the guard page. And because the U bit is not set, we're going to get a page fault or a trap into the kernel because the MMU cannot translate to address cannot translate any addresses on the guard page to a physical address because the not having a UMIT basically forbids the translation. Okay, and what is then page 2? Anybody?
The stack?
Yep, that's the stack page. And so again, the stack page is 4,096 bytes. And see that's pretty elaborate in terms of permissions. It has everything. Could we set it up tighter if we wanted to?
Yeah, I think you could disable the executable bit.
Yeah, you probably could execute the X bit. That would forbid having any program code on the stack. So if you generate code on the fly and put it on the stack, you wouldn't be able to execute it. That's maybe probably a good thing. And so we could have been a little bit tighter. Okay, so that's basically the bottom part of this thing of the page table. So now let's look at the remaining entries. So there are basically only 2 remaining entries, and maybe the flag bits are the most telling part of this. So 7, means read, write, and valid, right? And so what do we think that one is? And maybe I'll do the other one too. So B is, I think, 1001, so presumably X invalid. So what do we think 511 is? Anybody?
The trampoline and trap page.
Yeah, so that's clear. That's the trampoline, and probably 511 is definitely the trampoline, correct? Because it has the X bit set. So we must be executing, or we're allowing instructions to be executed from that page. So that must be the trampoline, and we're allowing read and write, to that page. So that's probably the trampoline page because that's the one we use to restore and save registers in. Okay. One of probably the most important thing to notice is there's no U bit. Right. And so what does that mean? That means that the user program can actually not execute the instructions that are actually at 510 and at the trampoline page, and can't read and write to that page. So only the kernel can execute instructions from there, and it can only read and write.
So basically, like the kernel is going to be doing this before the while still using the user page table, right? That's kind of the point.
Yeah, exactly as we, sort of Robert explained in the last lecture. This is like just for the transition from user to kernel, and before we jump to before we load the kernel page table in the SATP register, we need a little bit of, the kernel needs a little bit of memory to actually do its job. Okay, so a couple other things then may be interesting of this picture. Yeah, so we all these addresses, right? 87630, 8624, 719, these are all pages or memory in that range of the kernel memory that is not, that's basically free, right? And are these addresses contiguous? In physical memory? Anybody?
No, they don't have to be.
No, they don't have to be, and they aren't, correct? Look at this, 76400. If we're contiguous, then the next address would have been 876, 650, right? And it isn't. So there's one of the cool things about page tables is that even though maybe the virtual address space is contiguous, the physical address space or the physical pages that go along with the contiguous virtual addresses don't have to be contiguous. And so this gives the kernel a lot of flexibility in terms of allocation and freeing pages. Okay. Any questions about this part one?
I had a question.
Yeah.
Could you explain the SBRK a little? Also, if we are going to cover it in a future lecture, then maybe we can, like, just a small.
Yeah, actually, I'm going to talk about it on Wednesday, and it actually will be the topic of the Lazy Lab. And so let me maybe postpone that question a little bit to Wednesday, and then if that's not clear enough, please ask it again.
Sounds good. Thank you.
I also had a question.
Yeah.
So I remember that the book said the trampoline and the trap frame were at the top of the address space.
Yeah.
But here it stops at like the root page table. It indexes at 255, not 511.
Yeah, brilliant question. Very good. I'm glad you asked it. I saw it in the Q&A questions, and I was planning to talk about it, but of course I forgot. So yeah, what's going on here? Why is 255 not 511? Yeah, we always say the trampoline lives at the top of the address space. Well, the top of the address space, correct, is is actually entry 511 of the top level directory, and it is only 255. Anybody, any ideas why this is the case?
We said that one bit that we said we were going to use, we actually aren't using because of sign extension problems, because it just makes it easier, and we also don't need that memory.
Yeah, so so that's exactly the right answer. So this is basically stupid technicality. So the virtual addresses are in principle, I think 39 bits, correct? But we actually in XV6 only use 38 of them. And as a result, the top of the max VA for us is basically the 255 entry. And the reason we don't use the 39-bit is for no particular good reason other than that basically if you have the 39-bit set, then all the remaining bits in the 64-bit address have to be ones. And so we just didn't want to deal with this problem that if we ever set the 39-bit, we also have to set the 40, 41st, 42nd, and 43rd, etc. until the 64th. So that's the explanation. Does that make sense?
Yeah.
That's a very good observation, Joe.
Sorry, I also had a question about why is the text and the data on the same page?
Very good question also. That seems stupid, right? I mean, why not put them on separate pages so that you can actually set the permission bits more carefully? The main reason we're not doing that is for simplicity. It just makes exec more complicated, and we wanted the simplest exec possible. So a real operating system would not have data and text in the same page. In fact, we have to specify, if you look at the loader flag in the make file, you'll see that it has the -n option, and that forces is actually data and text to be in the contiguous and not in separate pages. Any more questions about this?
I had a follow-up question regarding the number of bits we're using. So you said we're using just 38 bits.
Yeah.
Is like the hardware still provides for us to use 39 bits, but we are designing our operating system such that we're using 38.
Yeah. So we basically, if the machine had more RAM than 2 to the 38, we would not be able to use that RAM. Now, we're already running with, we're assuming basically much less memory than 2 to the 38, so it's not a big deal for us. But a real operating system would have done better. So just pure for simplicity. We want to make it as easy for you as possible by reading the fewest lines of code possible. Okay?
Yeah, makes sense.
Okay, so now let's switch to part 2. And so let's bring up, a picture you probably have looked at a lot. The kernel address space, correct? On the left is the virtual address space, on the right is physical memory. Here are I/O devices, and then from here on is DRAM, and and basically running until what actually 128 megabytes for us, because we just assume that there's no more than 128 megabytes of memory. And so this part of the physical memory is the free memory, and from that is where the kernel. Oops, I drew it a little bit wrong. Let me be a little bit more careful. So here we basically have kernel text and data, and then this memory above is basically memory that the kernel allocator has, and from there we allocate memory for user programs, we allocate memory for page tables, etc. The kernel allocates everything from there until it runs out of memory. When it runs out, it gets to 128 megabyte, and then it starts returning errors or system calls. Okay, good. So let me pull up my first part, correct, in some sense of this assignment. Was the part 2 of the assignment was just to run with or copy the kernel page table so that every process has its own kernel page tables. And that was basically that's the assignment here. So let me, before jumping into the code, let me actually say a couple things, more general things about it. So part 2. And maybe the first question really to sort of get your head around is like, in some ways, this sounds trivial, correct? We already have a kernel page table. We just have to make n copies of it, for one copy for each particular process. And you might say, well, how hard can that be? And it turns out, it's a little bit harder for a couple of reasons. Some good ones, some less good ones. Harder than it seems. And one reason is that the x86 code is sort of specialized for one kernel page table. And you saw that in KVM init, and so that makes it a little bit. Generalizing, is actually a little bit of work because you actually have to modify the x86 code. KVM init, as you also saw, is not the full story. For building the page table for the kernel, there's also stuff in proc init that actually adds mappings to the kernel page table, and then there's even something in virt.io disk that actually interacts, with the kernel page table. So basically, there's no one single place in the kernel where actually the kernel page table actually is built. Then the third reason why this is slightly complicated is because you also have to deal with cleanup. So there's the aspect of actually creating these copies, but whenever time a user process exit, we also have to clean up those page tables that were in use because we want to return them to the pool of free memory so that we can use them later. So that we can keep on running processes. So that is And that makes things a little bit complicated because, you know, we got to be a little bit careful in actually freeing the kernel page table or a copy of the kernel page table. But we certainly don't want to, you know, free memory that's actually still in use or page table entries that are still in use by other page tables. So we got to be careful there. And then, you know, basically it's easy to make a small error in your page table when you copy those page tables. You know, if you get a little thing, you know, basically you get a hard bug. And one of the problems here is, as I said a little bit earlier, is the hard bug shows up much later. Right? You built the kernel page tables, or you built a copy of the kernel page table. All looks fine. You load it in SATP. Then maybe the kernel runs for a little while, and then it panics. And it turns out, you know, the reason it panics is because, you know, you made some small mistake in the page table a long time ago. And so that's sort of one reason why it makes, you know, makes life difficult for kernel programming. And, you know, and basically, you know, these hard bugs basically are just time consuming to track down. Because at the point that the bug happens, that's actually not the real cause of the bug, but the bug, you know, the real cause is, you know, someone way earlier when you set up the page tables. Okay, so it turns out there's sort of two approaches to go about it to this lab, which is sort of two solution approaches. In fact, some of you have probably used a mixture of them. But one, you know, approach, well, I'll call the copy approach. And the copy approach basically literally makes a copy of the kernel page table. So every time you need a new kernel page table, you allocate pages for the page table, you fill them in, et cetera, et cetera. And that's one approach. The second approach is basically to share you know, the kernel page table. And in this case, what you do is, like, instead of trying to make a literally nice, clean copy of the kernel page tables, you share all the entries that are basically are going to be unmodified. You know from the assignment that basically anything above claimed or the duplicate address is actually going to be unchanged or unmodified. You know, there's nothing you have to load there in part 3. So you know that basically all the entries from above 0 are going to be probably identical. And so you can share those entries if you will. And so both approaches are, I think, perfectly fine. It's not abundantly clear, you know, which one is the better one. My solutions take this approach, and I don't really have a great justification for it, other than maybe you know, partially laziness. I didn't want to think too hard what's in the kernel page table, and so I figured, well, all the things that are going to stay the same, why don't you just copy them over, or you know, copy the PTEs over, and then I don't have to think too hard what actually is in that part of the kernel address space. And you know, leads to short code, but you know, I'm not sure it actually is shorter than, for example, the copy solution. But it's important to realize that basically there are two different ways of going about this particular problem. In either case, you know, whatever approach you use, you know, there's sort of an implementation strategy to it. And you know, the implementation strategy that I use for almost any kernel program is to do everything in baby steps. So I might have sort of a general plan in my head about how I go over the whole, you know, all the changes that I want to make. But once I start making those changes, I do like 1 or 2, and then make sure that those work first, and then you know, keep going. And the other thing I do is mostly, you know, just a strategy is keep the existing code. And don't really modify it, certainly not initially. I just add code and switch to this new code, and then do little baby steps. And the reason I'm doing that is so that I can easily compare old to new code. And I always have a working old solution that I can just, you know, roll back to. So in case some strange bugs happens, then I can go back maybe 1 step and then try again and sort of figure out, like, actually where my reasoning was wrong. But basically, you know, baby steps. Partly because these bugs are so hard to track down. Okay, let me switch to my code. So maybe start in vm.c. So here's the existing KVM in it. And actually, can everybody see the code? Okay. The assignment that we were asked for, correct, is to make a copy of it. And the way I do that is, let me see where that is. So here's my UVM create. That is the boring part. That's basically creating, allocating the top level page directory, so the L2 page directory. And then here's my KVM, the sort of equivalent of KVM in it. So I get the top level page directory here in this site. Then basically I copy the top 511 entries from the kernel page table that was already set up by KVM in it. And so that gives me most of the kernel page table. And then I just have to map in all the devices that live in the zero entry, because the zero entry is the entry that we're going to modify later, or we're going to map the user pages into the bottom. And there's a couple devices that live in the zero entry, and those devices need to be added to this per process page table, kernel page table. And so maybe if I go back to this picture earlier. So let me put up the kernel page table again. Yeah, maybe this picture is good as any. So if you sort of think about my solution, I basically, these entries, I just share with the existing kernel page table. So I don't have to allocate any L1 or L2 or L0 levels. They already exist. And the only thing I do is basically literally copy that PTE entry. And so only the bottom part, or the bottom entry, that is the piece I need to actually rebuild or copy explicitly instead of copying PTEs. And that covers the bottom 1 gigabyte, right, of the address space. And so one page covers 496. And so this, this entry, covers 512. Oops. This is then 2 megabyte, and this is 1 gigabyte. And basically, only one of these entries I need to fill in. Does that make sense? So returning to my code, basically, that's all I do in KVM create. And in my KVM3 is maybe not maybe cleanest solution, but I take full advantage of the knowledge that I don't have to do anything from the entries 1 to 5 and 11 in the top page level directory. The only entry I have to do anything about is the bottom entry of the kernel of the top level directory. That points to one L1 entry, and in that one LN1 tree, I just need to go through and free all the L2 or L0 entries. And in the end, free the L1 and then the kernel page table. And so that's my KVM3 and my KVM create. So that allows me to create a kernel page table per process, and then free it when we're done.
Sorry, quick question.
Yeah.
Could you explain again the reasoning for only using 1 to 512 and not 0?
Yes. Okay, so maybe the easy thing to do, actually, let me go back to the picture here. So we have our kernel address space, correct? And this is 0x8000, blah blah blah. In what entry does 0x00 fall into for the top level page directory? It's like the
0th entry?
no, not the 0th entry, correct? So whether we know what, so the zero entry, like this entry, how much does it cover this entry? How much address space does the bottom entry of the zero entry of the top level page directory cover?
I think Clint is it's free between 0 and 0x2000.
Yes, okay, so maybe I'm going to do it. I think you're absolutely in the right direction. So the bottom entry covers 1 gigabyte, correct? And we know, yeah, so like maybe I can, so the bottom entry is 1 gigabyte, which in that 1 gigabyte is the Clint and the Plick, correct? The UART and the VirtIO disk, I believe. And then Kernbase actually already sets up in a higher entry, right? And we could compute it if we wanted to. We could take 0x8880, correct? Shift it 12, shift it 9, shift it 9. And I think, I don't remember at the top of my head what it is, but we could try to figure it out if we want to, actually. Maybe we'll try. This is always very risky to do in lecture, but so GDB, I need to, so let's go to layout. Here's Kernbase. So we could print, so shift this 12. That gives us the that offset. Oops. Okay, that is that. So then we'll shift that guy. I think you can say this 9. Right, that gives us the next entry. One more. So this entry 2. Does it make sense? So we go back to our picture here. Basically, Kernbase is entry 2 in the top level page directory. Right. So, and we know from the third part of the assignment that basically we don't really have to worry about anything above Plick. And all that stuff falls actually in entry 0. Okay. Does that answer the earlier question?
Yes, thank you.
Okay, so now the only thing we have left to do is double check where we going to call this function kvm create, and that's going to be in alloc proc. So and that's so here where's the new process initialized, and I'm sure all of you do this exactly the same way. You entry, you allocate or you declare a field in the proc structure, and basically the result of it is actually what we stick in the kernel page table. Okay, and then the only other thing that we have to worry about is, of course, we need to use the page table, and so we need to look at the scheduler, and basically the assignment more or less told you what to do, which is before you switch to that user process, you need to switch to kernel page tables, which basically means loading the disk process kernel page table in SATP, and then when you're done switching, running the other process, and you come back from running the other process, and you're going to go back and run the scheduler, you got to switch back to the main kernel page table, the D kernel page table, because that's the one that actually is used by the scheduler. And why do we need to do this switch? Why is this important? Anybody?
So it picks the right kernel page table, because the SAT, when you go to the page table entries, it picks the right page table to pick from.
Hold on, let me hold on a second. Yeah. So okay. So when we stop, okay. Let me another way to ask this question. When is this kernel page table freed?
When the user process is done. So if we didn't switch, that would mean that we could be using a page table of a process that was being freed. So the page table was freed. So we don't want to be dependent on a process we're not running right now.
Yeah, exactly, correct. We can never free the page table of a process that's currently running. So we have to have some plan, to actually free processes at the point that they're not running anymore. And the wait system call is our way out, basically. Wait calls, looks if there's any children that are not living, that can be cleaned up, and then it cleans them up. But that means that basically when the parent process cleans up a process, we got to make absolutely sure that that the page table that is loaded in the SATP register is not is not that process page table we're actually currently free. Now it could be the case that there's no process running at all, correct? And so the scheduler basically has his own page table so that all processes can actually be cleaned up. Does that make sense?
Sorry, I had a question. Is it that you're mapping the CLINT into the new process kernel page tables?
Yeah, I do.
Why?
Because I think the assignment said like I only have to user processes will not be bigger than the client. Was that it? Oh no, I mapped both the plick and the client. Correct. And so, but I think the assignment told us that. So what is the lowest one? I think the plick is the lowest one, and basically the assignment told us that the user process will not be bigger than the plick address.
Okay.
Just to make it easy, we could have done. We wanted to make it as easy as possible for you. Clearly, you could have done better if you wanted to, but that was the simplest thing to do. So you have to make a few modifications to get it to work. Any further questions?
I have a question.
Yep.
Is it possible that you can copy 0 to 512 and then every time you switch, so you're still using like the global root page table, except you only copy the first root page table?
Mm-hmm.
And every time you switch a process, you copy over the user's addresses over to.
Yeah.
Is that possible to do?
In principle, I think you could do something like that. So instead of basically doing when you allocate a process and free it, you could do it sort of dynamically during the scheduler switch. It seems complicated. That might be more costly because that means that every time you switch between two processes, you have to make a copy of parts of the kernel page table. And so that might be, in terms of performance, not an ideal thing. The assignment didn't really say anything about it. You might have timed out in user tests if you did that.
Okay, I was just wondering because I tried that approach and it was a bad experience. I was wondering if that was possible.
I can imagine, but I think it's in principle possible. You could just allocate a new page table correctly and switch every time, and then free it when you switch out. I don't think it's the simplest, but in principle it's possible. I think. Perhaps with some other modifications to x86, but Any other questions? Because the only other change that you of course have to make is a user trap ret. You got to make sure that actually you run with the process's kernel page table. Okay. Okay, so let's switch then to I guess part 3. So we'll switch back to actually here. Okay, so actually that's maybe not a helpful picture. Let me see. I just want to be here. Okay, so part 3. So basically what our plan is we have our kernel page table as before, and we have the plick entry sitting somewhere, and what we're going to do is we're going to use everything below Plake to actually store the user page table, or we're going to map the user page table into all the the user program actually in the kernel page table in the bottom. And that's the goal. And of course, the first question to ask, why the heck do that? Is there any, any advantage of it? And I think maybe the easy way to see why it might be interesting is to compare the copy-ins, the new copy-in and the old copy-in. So so what happens in copy-in, correct? When copy-in copies data from the user space into the kernel address space. But if the kernel does not have the user address space mapped, basically the kernel has to do this page at a time, correct? Because the pages in virtual address space might be contiguous, but in physical address space, they're not contiguous. And basically what the kernel does in copy-in, it basically translates the virtual user address into a physical address. Since the kernel has all physical memory mapped with an identity mapping, the physical address is also a valid kernel virtual address. And then it basically moves whatever part of that page, physical page, that needs to be copied, it actually copies it. And so if a data structure, for example, spans to a page boundary, like for example, the sysinfo struct that you used in lab 2, maybe it spans a page table boundary, and we'll copy like maybe some bytes from the first physical page and then some bytes from the second physical page. Does that make sense? So that's what the current copy-in does, and the goal was basically to get them to a new copy-in, where the kernel program doesn't really have to worry about the physical layout, basically, of the user address space. And in this new copy-in, we basically do literally nothing else than just copy from the user addresses straight into the kernel. And we don't really have to call walk anymore because we can rely on if we set up the page tables correctly, the page table hardware will do the walk for us. Right? And so that was the goal. And so that makes life for kernel programmers a little bit easier. Are there any other advantages to this approach?
Is it also more performant because the hardware is going to do the walking and not software?
Yeah, well, one way I think there are performance implications for sure. One way to think about this is that in copy-in, correct, if the kernel data structure or the data that we copy from user space to kernel space is big, we have to do that page at a time. Right? And every page we have to call this function walk adder, and then does the internal walking. And so this might actually be reasonably expensive. What examples, are there examples of where the kernel copies a lot of data from user space? Which system call might copy a ton of data from user space?
Right?
Yeah, right. When you write, you can give an arbitrary number of an arbitrary buffer of an arbitrary size, and the kernel may have to copy this into, for example, the file system or into a pipe, and so that could be reasonably expensive. The other thing, what is another advantage? If the user, we didn't explore that in this assignment, but we certainly could have. What is another advantage? So if you think about some of these this code here, correct? When it takes a structure out of user space, it copies the whole structure into kernel space. If user space is mapped into the kernel page table, do we have to do that? For example, if we have to update one field of the structure, so if the data structure is just mapped into the kernel address space, right? Then we can just like read and write, with store instructions to that particular data structure, and we can just update one field. Unlike what the kernel now does, basically, it copies the structure from kernel space to user space, and then maybe back out using copy out. Right? So if we map the user space into, or the user program into the kernel address space, we can just manipulate it much more freely than the way we do it now. Does that make sense in terms of motivation? Why many kernels actually have this particular structure where they map the bottom part of the user, or where they map the user program into the bottom part of the kernel address space? Okay. Okay, so let's see. Let me look at my code and see if I understand what actually I did. So there's basically one function that is the key, correct? Assuming we're building somewhere a valid user page table, and then we just have to map the entries from the user page table into the kernel page table. Or the processes kernel page table. So I have a function kvnet map user that exactly does this. And it's pretty boring, but there may be a couple interesting points to point out. In work, it has the same sort of interface as UVMalloc or whatever, where basically if you go from the old size up to the new size, page at a time, you find the UPTE, the pointer to the PTE for that particular virtual address in the user page table. Right. So if we look at the picture that we had a little while back, look at this picture. Basically, what this is going to return, correct, is we're going to walk the user page table, and we'll find, for example, the PTE that maps, that particular virtual address. And we get a basically pointer to that entry into the page table. So that's what walk does. And so if the thing is mapped, if it's is not zero, that must mean it is there. So this is just a check to double check that actually the mapping is there. We check this valid. Just like there's debugging help in some sense. It should be the case that it is valid. And then I do the same thing in the kernel page table. I look up that virtual address also in the processes kernel page table, but I call this time walk with 1, so that it actually allocates intermediate pages if necessary. And then once I got the pointer to the kernel PTE, I just copy the user PTE into the kernel PTE. So probably a lot of you called map pages. But I just copy directly the PTE into the kernel PTE. And of course, I got to disable some bits, which we'll talk about in a second. But the essence of it is I just copy the kernel page, the PTE entries. And so that means that, for example, all the physical memory for the user program is just shared between the kernel space and user space. Okay, does that make sense? Okay, so then in terms of switching up some bits, I'm a little bit more than necessary, but I switch off the execute bit, I switch off the write bit. This copy in only needs to read, it never writes to it, or copy out does that. And then you have to switch off the U bit, and that is sort of RISC-V specific thing that if you're running in kernel mode, and the U bit is set in the PTE entry, the kernel can actually not access that particular page. And in fact, you can, this is almost a choice. You can also actually program the RISC-V hardware that basically in kernel mode, it ignores the U bit. But x86 doesn't do that. And so you have to switch off the U bit. Any questions about the U bit? Because there were quite a number of you who asked about it.
So is this done just to make sure that the kernel doesn't do anything bad to user memory?
Yeah, so why is this the case? Now, is this, so the question is like, is this for debugging reasons or is there sort of an isolation reason to do so? And I think this is mostly for debugging reasons because the kernel is in full control anyway, right? So the kernel can change the SATP register at will. It can disable paging as it wants to. So it's not like, the user space is protected from the kernel. I think it's mostly to basically help kernel developers. So for example, in x86 case, correct, unmodified x86 should never dereference a user page, period. And so that, and basically this just helps, if you happen to do that by accident anyway, you would get immediately a page fault and or kernel panic, and that, will help the kernel debugger or developer to debug the kernel. Does that make sense?
Yeah, thank you.
I have a follow-up question to that. I think the part about the user bit makes sense, but what about the write and execute bits?
Yeah. So does the execute bit have to be on? What does the kernel do with this page? It only reads from it, right? The only instruction that basically grabs data from this page is this memmove instruction in copy in. So it only, does execute load instructions from it, or loads values, from that particular page. And the page should only contain data. So there's no reason that the kernel should be writing to that page. And so just to be conservative, I disable the write bit. And the kernel should never execute instructions from that page. So I disable the execute bit too. And again, this is mostly, I think, for debugging reasons, not for isolation reasons.
Okay, makes sense. Thanks.
Okay, so now the only thing we need to do is basically there's a bunch of places where this code is being, or this function is being called. And we need to sort of look at these places where it's called to, so we understand what's going on or how it should be used. And I think maybe one of the interesting ones that a number of you asked about is fork and exec, and we'll talk about both of them. But first fork. So here is the call to fork, or the call to KVM map user in fork, and it takes the end. So the main interesting question I think a lot of you asked is, why does it have to be the new process kernel page table? Why does it have to copy from the new process page table instead of from maybe the current process page table? Because it's anyway an identical, right? When fork basically does, it just replicates the user part of the page table. And so why can't we use the current page table for doing that? And why, and actually turns out the case, you actually have to use the new, the child's user part of the page, the child's user page table. And why is that the case? Who of you notice what bug do you get?
Wouldn't you get a remap error?
You could, maybe not a remap error. Well, the thing, maybe that too, but the bug I'm thinking of is not the remap one. A number of you tried it out. What was your personal experience? Anybody on the call who tried this out and remember what the resulting experience is? I think the resulting, I did not have the bug, but I think the resulting experience is that somewhere in user test, particularly user tests that do a lot of forking and exiting, you're going to get a problem, and you get an error. And the error, the thing that goes wrong is that if you copy from the parent process, if the parent process exits before the child process does, then the parent process page table will be completely cleaned up, right, as we saw before. But then the child still has pointers, you know, to the parent process page table. And so basically you're gonna be pages in this child's process page table have been freed and they're still in use. And so that results in all kinds of bad behavior because the kernel, when it frees a page, actually writes ones in it everywhere for debugging reasons. And so now basically you have invalid, you know, PTEs sitting in your kernel page table. Does that make sense? Okay, one more thing to look at is exec.c. In my solutions are pretty straightforward. I almost made no modifications to exec. The only exec modification I made is, of course, you know, the first thing for, you know, part 1, and then here for part 3, it's just basically mapping the new user page table into the kernel page table. And exec basically what it does is basically builds a new user address space, and, you know, there's one line copies that new user address space into the kernel page table. And that's it. Any questions? So I hope in the meantime, I've answered many of the questions that you submitted, but we can look and see which ones. There were a couple more questions that I haven't talked about yet. So maybe we can look at those, or unless you have questions right away.
Don't we modify the grow proc as well?
Yes. Yeah, there are a couple more changes that necessary. You know, in SBreak or GrowProc, there's a, I added a line right here of very similar style, and there's presumably a similar change in, I think that might be it actually. Oh, user init, of course, probably has a change because you have to map that one page from the init code into the kernel page table for that process, because the first process is special. Okay, so I'm going to walk through some of the questions here that I put them on the screen so you can hopefully see them, so that I don't have to read them out completely. I think the first question is a question that actually came up quite a bit about the PTU bit flag. I think we've covered this. We also covered the fact that it's not malicious, but it's mostly for debugging reasons. Similar question about, like, well, if you're in supervisor mode, can't you do anything? Because you can switch the SATP, you can, and the answer is yes, it's all possible. So again, really, you know, this UBIT is not about the user program being protected from the kernel. It's really as a flag to help the kernel developer build the kernel. One other specific sort of RISC-V question, which is why are the in TrefFrame proc.h, why are the registers sort of in a strange order? And the reason for that is, I think we mentioned this a little while ago in a previous lecture, that there's something that's called the RISC-V compressed instruction set, and that has a set of fewer registers, and so that you have to have a more compact encoding of the instructions. This strange ordering reflects the fact that there are basically there's the compressed version, which is some set of registers, and then sort of the uncompressed version, which is what we're using, that has the complete set of registers. And the compressed version, the example, has S1 and S0, S0 and S1, but not S2 through S11. So that's the main reason. So I think I went through most of these questions, but if you see a question that I should have covered and I didn't, you know, please interrupt me, or if you ask a question that I haven't covered yet, please ask. These questions are basically in order that you submitted them. So these were Okay, here maybe, so here's our question. Do operating systems use hierarchical and page tables ever to set up the page table pages so that the lower parts of the hierarchy are at least partly shared? And you know, you clearly saw in my solution, correct? I share the entries 1 to 511. And so this is a standard trick, and lots of operating systems do that. I think we talked a little bit about this particular issue, that it's important that you switch to this main kernel page table, because the scheduler, there might be no user processors to run at all anymore. And the scheduler, of course, still needs a page table. And so it runs with the main kernel page table.
We have a question in the chat.
Yeah, go ahead. What is the, let me pull up the chat. Hold on.
I can read it if.
Yeah, I got it. So I think, okay, so the question is, doesn't the RISC privilege specs say that part of the separation is to prevent bugs that allow the user program to make the kernel jump to arbitrary code in user space? Yes, that's a good point. And so, you can debate here whether this is an isolation property or a kernel debugging property. Clearly, the kernel should never jump into any part of the address, the user address space directly. And so, I view this as a tool to help the kernel debugger catch those kinds of bugs. And in some reason, that's why in XV6, we also disable or set the view bit and don't allow the kernel to refer to any pages. That protects us. If we did reference ever a user address, that the kernel would actually fault. I think I covered the scheduler point too. So here's a question: how are pipes implemented in XV6, and should the change to page table implemented in the page table app affect this implementation? So pipes are basically a buffering memory in the kernel, and when you write to a pipe, basically calls copy in, and copy in copies the bytes from user space into the pipe. And in some ways, the whole part of this page table app was basically streamline that code so that you don't have to do many walks when you actually write from user space into the pipe. This is an interesting question. I think a lot of people ask you, like, why does UVM3 and FreeWalk originally panic at the leaf? And the reason is that we put that panic in there because it broke. That was an indication that an invariant in XV6 would be broken, and that's the invariant for unmodified XV6. In this particular case, that is not true, and so you have to basically get rid of the panic and realize that it was not important to panic there, or you should not panic there. I think we talked quite a bit about why VM copy new is, why the new VM copy is a good one. Okay, here's another question. Let's say, and this is maybe an interesting one question that was asked, a sort of more design question, and maybe it helps to have a picture. We look at the kernel address space, right? We limit it. Let's see if I can find my pen. We limited user programs can be bigger. We said basically user programs can grow to the client address and no further. Let's say we actually wanted to grow all the way to here. How could we do that? How should we change the design that would allow that? Anybody?
Could we remap the stuff like Clint and BLIC and UART?
Yeah, where would you map it? So where if you wanted to free up basically that part of the address space, what could you do?
Map it to a custom thing before kern base and after, before physical stop and after kern base.
Yeah, or maybe actually better to after fish stop, correct? Here's a huge amount of free space, like address space that's unused, correct? This from here to there is basically used for physical memory. And we basically could set up mappings here, correct? For example, we could put the UART here, like UART 0, we could put it just above this page and basically set up a mapping that maps to that particular physical address, right? And then that will free up this mapping and we could use it for user space. And so similarly, we could do that for UART 0 or for VirtIO disk, for Plik and Clint. And real kernels do that. Does that make sense?
Isn't that problematic though? Because we want the same mapping as the original kernel page table has.
Well, we have to do it in every kernel page table, correct? If we have copies, we have to map it everywhere at that particular location. I'm not sure that answers your question, but I don't think that's a problem.
I see. So you do that mapping also in the original.
Yeah, we would have to do it also in the original one. And that's easier, like if the whole kernel uniformly thinks about UART 0 sitting on the top. Yeah, a number of people ask this, like, why do we map the kernel stacks high up? What is the reason for that? Like, so in proc init, correct, we map these kernel stacks high up. And if you did the copy approach, you actually have to modify proc init to actually copy over that mapping. And why sitting it up high in the virtual address space? Anybody?
Is it specifically because the stacks in RISC-V grow downwards, and so you place it high in the address space so that it has space to grow downwards?
Yeah, how much is it the right direction? How much space does it have to grow downwards?
That shouldn't matter because it's just one page, right?
Yeah, it's only one page. So what happens if you grow beyond one page? You run into the guard page, correct? And the guard page is not mapped. And so the kernel will panic, which is better than actually writing over its data structures. And so the reason it's high up is because we put a guard page below it. Is there actually any physical memory associated with that guard page?
No.
No, there's no physical memory associated with the guard page. Right? So that's one of the cool things about putting it high, is that we can put a guard page below it that actually doesn't consume any physical memory. Okay, does that make sense?
Oh, so basically the kernel stack page will be physical somewhere, but the guard page won't.
Exactly. Again, one of the cool things you can do with virtual memory.
Is it possible to overshoot the guard page?
Yeah, that's a great question. What for example, if you allocated the guard a buffer on the stack that actually is way bigger than the guard page, correct, and sort of goes into the next kernel stack page, and yeah, then you would have a serious bug. Most likely, you will run into that anyway, right? Because you presumably would use the first entries of that buffer, and then you would get the page fault. But you could get it lucky. So this is not a bulletproof kernel debugging technique, but it has proven to be extremely effective. Great question. Any more questions? I'll go back to the list. See, we have a couple more minutes, and then actually we have one more minute.
I have a question.
Yeah.
So once we have our kernel page tables for the processes, does it mean that in the trap code, we don't need to switch page tables?
I think that's a great question. It's a good design question. And the answer is yes, you don't need it, right? Because the main reason that the kernel or in the trampoline code we go for all this trouble is because we have to copy the user. We have to switch from the kernel page table to the user page table, and the user page table, or that page table doesn't have the rest of the kernel mapped. And so the downside. You know,
Wait, I'm not sure if that's true because the kernel needs to have the user flag on set.
Yeah, okay. So there's a couple of points I wanted to make. So in principle, you could simplify the let me put it this way. You could simplify entry and exit if you have a single page table that maps the user and the kernel in a single page table, because then you don't have to switch. You will have to make a couple more modifications to x86 to make that happen. But in principle, you could. And in fact, Linux, until very recently, used this sort of strategy of where the kernel and the user code are sitting in a single page table, and relying on basically the U-bit, to make sure that the user program couldn't actually modify any kernel pages. And the entry-exit code in that case is slightly simpler because you don't have to switch page tables when you enter or leave the kernel. One thing that happened with, for example, the meltdown attack, if you might have heard of this side channel attack, in response to the actually side channel attack, Linux switched or has another mode of running. There are two modes of running. One is called the KPTI mode. And in that mode, basically, that reflects basically what x86 does. Having a separate page table for the kernel and a separate page table for user space.
Wait, so I still don't understand why that works. So let's say the user process and the kernel use the same page table. If the user memory has to have the user bit set, the kernel will not be able to access that user memory, right?
Okay. On Intel processors, that is not the rule. So, for example, on Intel processors, if the U bit is set, the kernel can still write and read that page.
Oh, that's just a RISC-V thing?
And even on the RISC-V, you can change it. There's a bit in the S status register that you can set, the sum bit. And if you set it, then basically in kernel mode, the U bit is ignored.
Okay, so you're telling me that there's just one bit in this CMU processor that made me stay up 4 hours later.
Yes. I'm very sorry about that. I should have realized.
No, it's okay. It was a fun realization.
When you reported it, it reminded me of a bug that I actually had during the summer, and it was exactly that bug. But I've forgotten about it. So my apologies for that.
No, it's okay. It was fun figuring it out for sure. But I at some point I was just like, okay, like either I'm crazy or something's completely wrong. So I'm just gonna go to sleep and submit this Piazza post, and hopefully when I wake up, someone will answer. And fortunately, that was the case. So I was able to just continue right off when I did.
Okay, so I think we ran over time a little bit, but hopefully this was helpful and reaffirms things with virtual memory. I think it was important to do because we're going to get 3 more labs involving virtual memory. And my hope is that after this one, those are going to be easier than this experience.
Can I ask something very quick?
Yeah. I'm staying on, so everybody wants to stay on and ask more questions, please feel free to do so. If you need to go to the next class, please go.
So basically, in all the labs, like there's a lot of mention of like, oh, this might be useful in future labs, but we never actually use any of the code that we write. Like, what's the plan on that? Like, should we just import our code from a previous lab, or like I don't want to, because what if it's buggy? I don't want to, impact the next lab.
Yeah, so the one reason we don't do it, why the labs don't build on each other, even though they could, is to avoid basically dependencies. Like if you had a bug in an earlier lab that was not exposed by user tests or any of our tests, but would be exposed in that new lab, then it would be painful. The reason I'm mentioning that is that basically the real thing of what's going on is we're going to do more stuff with page tables. So for example, this lab looks at simplifying copy in. Later labs look at changes to SBreak. They're basically orthogonal to the changes you made to the kernel for this lab. But the fact that you've been thinking about kernel page table and user pages table so much will help you. Plus, really what helps you is sort of the experience of debugging these kinds of problems due to incorrect page tables.
Okay, I just wanted to make sure that it's not like I'm missing out because I didn't copy over my Xarch code from lab 1 or something.
Decided on purpose that the labs are not dependent on each other.
Okay, thanks. See you on Wednesday.
See you Wednesday.
I had a follow-up on my question about mapping using the modification from the page table app. Would it be then needed to have the trampoline mapped in the user page tables?
Okay, so I haven't really thought this through. So if the kernel, let's say the kernel exits, so let's say we have a joint one single page table as the one here shown, correct? And we're jumping out of the kernel through user ret. And our goal is to, we're still running in kernel mode. So this page certainly accessible, correct, by the kernel, the guard page. Oh, sorry, not the guard page, what I'm saying. The trampoline page is there. And presumably somewhere we need to map maybe the, well, the user trap frame, we don't really, we have access to anyway, right? Because we're running kernel mode, we know where it sits in the proc structure or we can get it. So I think we can just exit. And when we return, then the user code can just run. You know, of course, the UBIT is a bit of a, well, the UBIT is only set on pages that actually sit in the user space, so that's fine too. So when we enter the kernel back in, you know, we're still with this page table. That page table already has all of the kernel now mapped, and we could just, you know, copy, you know, the registers that we need to save into the proc structure directly, instead of having to go through the, have a separate page with the proc struct in it. So I believe the change would be pretty straightforward.
Okay, I see. Thank you.
But, you know, of course, I could be wrong.
Oh yeah, I'm now gonna try it now.